Perfect.
Hello, everybody. Thank you for joining us for the 21st session of Super Spreader Seminar Series on 28th of March. As always, we have land acknowledgement. We acknowledge the land of the OMNI-RÉUNIS Network head office is located on York University. Recognize that many indigenous nations have long-standing relationship with territories upon which York University campuses are located that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many indigenous nations. The area known as the Toronto has been caretaken by Anishpac nations, Haudenosaunee, Confederacy, and Huron-Wendat. It is now home to many First Nation, Inuit, and Métis communities. We acknowledge the current territory holders, the Mississauga of Credit First Nation. This territory is subject of the dish with one spoon Wamput-built convent, an agreement to peacefully share and care for Great Lake regions. Super Spreader Seminar Series. The OMNI-RÉUNIS Super Spreader Seminar Series stands for SSS, welcomes faculty members, OMNI-RÉUNIS affiliate, and highly qualified persons, including postdoctoral researchers and graduate students, to showcase their research, promote their ideas, share their research experience, and establish connection among the various branches of network. It is a platform to spread scientific knowledge about the One Health research framework and the research progress of over 30 OMNI-RÉUNIS HQPs within the network scientific research community. These seminars facilitate knowledge exchange within the OMNI-RÉUNIS, the emerging infectious disease modeling network, and the collaborating scientific community. Today, I'm happy to say that we have Haysn Hornbeck. Welcome, Haysn. Thank you for accepting our invitation.
Oh, no problem.
Great, thank you. Haysn is a PhD candidate in computer science at the University of Calgary under the supervision of Usman, Alim, and Rob Deardon. His primary research in disease modeling through the use of Bayesian model with secondary interest in computer graphic visualization and cryptography. Great to have you today. And he's going to talk about stand data annotation, automating probabilistic programming. Probabilistic programming is a growing field thanks to the availability and refinement of powerful tools to perform Hamiltonian Monte Carlo. This has created a need to automate and streamline the creation of those models. Stand data annotation, stands for SDA, was designed to fill that niche. It is both a simplified environment for writing stand models, freeing researchers from having to write programming code to handle basic tasks like data retrieval and filtering, and a toolbox for automated execution of stand models. This seminar will talk about the design of the system, the current state of the implementation, and the future plan for it. Thank you, Stan, for accepting our invitation, and I would be thankful if you share your slide.
Oh, I'm working on that now. And I want this one. Excellent. All right, you should be able to see my screen now.
Yeah, it's perfect, completely readable.
Sweet. All right. So yes, I'm going to be talking about stand data annotations. If you want to jump ahead, there actually is a link to the Git repository sitting at the bottom there too. So feel free. The origin, obviously I'm going to talk about the origin, sort of goal and structure of this thing as well, and show off what I've got currently at the moment. The origins for this actually sort of started right around the beginning of the pandemic itself. It was a project out of Britain to sort of rapidly give disease modelers access to private health records without actually sort of revealing what those health records were. The way they actually sort of did that is you would actually take sort of your model and given an outline of the day, you'd submit to some sort of central repository, which would run on the data and give you the results back. Since you never personally sort of saw the results, you actually, it's protected patient data, and you could still sort of get meaningful impact out of it. It's sort of, thought about how you could potentially build such a system, sort of an automated thing and all that. Not much sort of came of it, sadly, but fast forward a couple of years to my work with the dashboard for OMNI Group as well too. I sort of created this basic, thing that allow you to sort of visualize data on there. And one thing, of course, was visualizing models we could actually sort of throw on top of that as well too. Now, once you've got the ability to visualize the models on there, there's an obvious next step that Boucher gave me to actually create the models on the fly itself. The requirements that we were looking for is that we needed some sort of simple language, which, pretty much anyone could sort of use and understand to actually build these models. It's obviously got to be able to interface with the existing dashboard in order to sort of move data back and forth and update the models proper. And also it should be able to automatically update as new data comes in, because presumably, these data sets that are being stored are being continually refreshed as, as they're sort of updated, more case counts and all that were coming in. There needs to be some way to actually automatically trigger updates and, automatically update the projections as they come. And with that, I'm like, okay, this is now two instances where a system like this could be of use. This is something which probably could be used outside just the dashboard itself and maybe used for, much wider things and all that. So I sort of tweaked the requirements to be a little bit more expansive, to slightly different goals, essentially. The language for expressing models, that was a constant right there. But instead of just interfacing only with the dashboard that we were building, I wanted something more generic. It could basically interface with any sort of external data source. This could be, limiting it just so it can only access the dashboard proper, or data sets stored within there. Or it could just pull in arbitrary things off the internet, or local sources too, whichever one that's there. Instead of, just having something which just triggered automatically the updates that are coming in, make the entire system much more modular and extensible. So people could actually take, the basic template that's sitting right here and create their own variations of it, and do more than just simply automatic updates. Potentially sort of, run various different versions with different parameters and all that to see how the different models fly, that sort of thing. Basically turn into almost like a playground for modular, for model testing. All right, well, this means now we're sort of on the hook for finding a simple language for expressing models themselves. Now, the obvious thing is to sort of come up with your own language. This is a terrible idea because now you've sort of got a learning curve for people to actually figure out how this language works, how to express things within it. Even if you've got sort of the background knowledge of probabilistic programming and such in there, it's a huge pain. So wherever possible, do not actually create your own language from scratch. Find some way to use an existing one and use it as a submission for the system proper. Obviously, I am very focused on probabilistic models, Bayesian support Bayesian stuff as well, so that it must be able to actually support that as well. At the same time, while it's also tempting to write your own sampler, there's a lot of really good ones out there. You can write it's very simple to actually write a basic Markov chain Monte Carlo sampler, but if you're going to do any sort of serious work with it, it gets writing a fast, good sampler, it becomes very tricky very fast. So what can we use for a backing sampler for this? Just setting aside the language thing for a bit. I've had good luck with MC in the past. It's, I think, got a good decade-long track record. Used quite a bit in the astronomy research area as well, too. To give you sort of some example of how exactly you would create a model like this within MC itself. Here's a classic example actually pulled from the MC website. Standard linear regression. To make things a little bit less boring, though, each data point actually has an error bar associated with it. We're now trying to figure out what exactly there is for a trend for it. It's just a simple linear regression kind of fit and all that. If you were going to create this within MC itself, you would basically just create one Python function and feed that into the MC engine itself. That function sort of carries all the probability information you've got and outputs a log probability at the very end. For a programmer, it's very simple and easy to use. But again, we're trying to get away from programming. We want people who can actually understand and write these mathematical models, not necessarily programmers, to come in and do it. You're also not sort of given a lot of tools to sort of work with here. Like, this all looks kind of confusing. It's only once you actually know the mathematics behind it, then you can actually realize, oh shoot, this is actually just a Gaussian model. But Dan Formanaki, when he was writing this, actually dropped a lot of the constant terms because he knew they wouldn't be in there. So it's nice and tight and streamlined, but it just, is not very intuitive at all. ironically enough, it actually runs fairly quick. It's only 4 seconds or so to get, I think it's 5,000 samples within there. So it's a sort of an underappreciated library in my opinion. It has some other advantages too, such as it's written purely in Python as well. So it's got very few dependencies, very tough to break, and tends to be very stable. But overall, a very poor choice because we're going to have to come up with our own language and sort of impose it on top of this. The next, sort of the next bigger one, in this landscape would be PyMC. This one has been around, I forget exactly how long itself, but I think it's going to be at least a decade at this pedigree for it. Overall, it's actually sort of one of the fastest and the most sort of fully featured within there. Quite popular within industry, as far as I understand. It takes a very different approach to this. Rather than just sort of let you write arbitrary Python code itself, it actually uses a Hamiltonian Monte Carlo sampler underneath there, under the hood, which means actually it wants gradient information with it. It gets this via two ways. One way is just by sort of forcing you to use existing components right here. So rather than write your own code to create a normal distribution, you just invoke the existing normal distribution that's right there. And that automatically brings in the extra information it needs to actually fit the model and fit it quickly. The other approach is something known as automatic differentiation. If you give it just simple mathematical things, it can actually do all the differentiation steps behind the scenes, intelligently. And because Python is such a flexible language, it can take just straight Python code and do all of the stuff behind the scenes to generate a proper, gradient that it needs for that. Now, because it gives you these sort of tinker toy things right here, this sort of moves closer to what we're looking for with the language. You can see how this does sort of map on fairly well, but we're still sort of running arbitrary Python code right here. And if you take a look, it actually took longer to actually fit this model than it did the prior one, even though the prior one was just pure Python itself. And this is a mix of C and various other things to sort of help accelerate it. This isn't to knock PyMC. If you go in and configure things, you can actually get much faster results for that. This is me just sort of installing the thing out of the box and not doing much tuning on it. Of these three major ones, though, the third one is Stan. It's, I think, a little bit more popular in academic circles and all that. If I was to actually to answer the linear regression thing, I would actually write something like this. This is not programming code. Not really. Well, okay, it is and it's not. It's actually its own specific language for this. You can see it's actually got, normal distributions and all that sort of pre-built in within here. But also it takes some of the syntax you would use when actually writing out your model itself and uses it within there. So for instance, it's got this little squiggle to say, hey, I'm pulling from a random distribution. There is, obviously a little bit of code here, but it's much simpler overall. You're not dealing with an arbitrary programming language. This is something tuned specifically for integration and all that. So, if we actually were to go with Stan as sort of the backing, sampler for these probabilistic programmings, then we basically get the language for free, which, is great. We don't want to invent a language out of scratch, as mentioned before. And this language also has a bit of a pedigree. It actually had its origin within bugs. This is an older sort of sampling package. I think it dates back about 35 years or so. And it also had its own sort of programming language where you would go on and specify your own model. The syntax has changed a little bit over the time, but it does have a very strong sort of pedigree to it. And a lot of people have actually used this. You may not know it under the name bugs, but instead WinBugs, which is its most popular variant. But it actually did have a big impact, and it was quite popular and all that. So this definitely seems like a good choice. And best of all, if I actually run through that program there and get an answer, it's the fastest of the three by a decent margin. I get an answer, I get all those samples in under a second. So not only is it fast, not only does it actually come with an existing language, but that language actually meets a lot of what we need for our security needs. There is no real sort of file system or device access to it. It's really just sort of like a little enclosed environment. Nothing specific to that. There's no way to actually sort of import other code and all that, so you can't have attacks, that involve that. There's no support for binary operations. It doesn't really support characters. There are some print statements which you can use actually to print characters, but it doesn't actually support it as something you can manipulate. It's almost just like a constant you can sort of spit out. And again, the language has been around for ages, so this is not inventing something out of whole cloth. And other advantages as well is, in fact, the language that you've got within here is Turing complete. So in theory, if if the tools that it provides you are not good enough, you can actually write your own within Stan's own internal language. And meanwhile, I am focused on probabilistic programming and specifically Bayesian work. You don't have to use it for that. In fact, the sampling portion is entirely optional. If you don't believe me, here's just a simple little program which will grind through and generate the first n primes for you. Just use a little bit of math and all that to speed things up. When I timed it on my workstation, it took about 9 seconds to generate the first 2 million primes. And even that's a little bit misleading because it spent about 4.5 seconds just writing to disk. So the actual computation was only about 4.5 seconds or so. So yes, you can use, even if this is, something specifically Bayesian, you don't have to use it for that. You could use it in a frequentist framework or for other things as well too. So it makes for an ideal source, but interfacing with external data sources, to maybe sort of explain that situation, let's go into what exactly Stan is. At its heart, Stan is really just sort of a library to take the Stan programming language and convert it to a C header file, a C+ header file. Obviously, this is pretty useless. I mean, I want to be able to sort of fit, my data within here and all that. And I want to be able to sort of read the posterior itself. And you're just, dumping me with a header file, not even like a proper executable. How exactly can, you accomplish anything with this? And the Stan authors, came up with a simple solution. They wrote a wrapper around Stan called command Stan. What this does is it takes that header file, in addition to sort of compiling it for you, and dumps it into an executable. This provides sort of like a simple wrapper that allows you to take your input data, in this case, say JSONs, in JSON format, grind through and run it with the parameters you specify, and output just a comma-separated value for the actual posterior itself. So that answers the input and output problem. But of course, it wants a JSON file of this particular format, and you're probably not going to be feeding it JSON files. Like almost everything that you feed it, you'd want to feed into these things are comma-separated values and all that. And, there's just sort of a lot of management stuff behind the scenes, which we want to be done, which isn't being done right here. So, the authors sort of thought of that as well, too. And a number of projects have sort of popped up, sort of, being like command Stan X. Now, there isn't actually any one command Stan X project. What I'm most familiar with is command Stan Pi, which is basically just a thin wrapper on top of command Stan, a thin wrapper on top of Stan. But there's also command Stan R if you're using the R language. There's also stan.ly for Julia and all that. And essentially, these are thin wrappers around command Stan, which allow you to take from a programming language of your choice, Python, R, Stan, Julia, and all that. Read in Stan files, run them through command Stan itself, and do all the execution stuff for you. Since we're now invoking an arbitrary programming language, we can pull in data from whatever source we want. We can also do all the cleaning and filtering that we need, the high-level management stuff to actually split things across different, files and all that, which is great, but we're back to writing programming code. The whole goal of this was to not write programming code. We want something, good idea, we want something else. What we really want is something like this. We take a Stan file, and it automatically, we hand it to some mystery black box or something, and it goes in and it reads all the data that we want. It'll do any sort of basic parsing and all that. It feeds it back into command Stan. And then once it gets the results back, it'll then take that output and split it into whatever format we want on the other side. That way, we're only ever actually dealing with one file itself, and we're sort of feeding it in. Now, obviously, Stan itself does not have any sort of support for anything like this, for actually puppeting itself around. So obviously, we're going to have to add something to the language itself, some sort of annotations to explain data, hence title drop right there. Okay, well, if we've added those extensions and all that, that kind of settles that thing. But there's still the original goal of having sort of a modular extensive design. And once we sort of hit, point 2, this part is fairly easy. We just sort of have to think ahead a little bit. When sitting down and actually writing this, we don't actually write it as sort of one big giant, monolith and all that. What we do is we actually sort of do a sort of a hierarchical kind of approach to it, where, yeah, if you want just to sort of run it as a black box, fine, sure. But that box is constructed of several sort of modules, which do their own separate tasks. And so if you want to actually override what one of them does, well, I mean, you write your own version of that thing and sort of, pull it out of the system and interface with the other modules. Those modules themselves are written in a very sort of modular kind of thing, where it's just a series of small, short routines which are sort of accessed and all that. And once you sort of understand the programming code itself, you can actually just pull those apart and actually go through the entire chain and process and modify things to your thing. So just by sort of writing the basic framework itself in a very careful, modular approach, we can just hit point 3 almost, for free, just by sort of thinking ahead in that regards. All right, and that's sort of the basics of stand data annotations itself and how it's sort of structured out. I can actually sort of talk through some of the examples themselves. I've also got a live demo to show off as well too. Since I've got plenty of time, I'll actually go through the more sort of slower approach to actually break down what exactly is involved with this as well. When designing stand data annotations itself, there's sort of 3 core principles I really want to try and follow. This must be simple and intuitive. Again, the goal here is not to sort of introduce another programming language on top of what people use. We are adding something extra, so there is going to be a learning curve, but we want it to be as simple as possible, and we don't want to assume people have, like a strong programming background. Again, so make it just, the very basics that we can sort of get away with. It also cannot break existing stand stuff. We are adding something on top of there, but what should still be underneath there is a stand program itself. That way there's actually sort of backwards compatibility. If, say, our annotations prove to be not good enough and you want to actually do it the traditional way with, a programming language wrapper, you can actually just go back and do that itself. It's not going to sort of change anything. This means then that a lot of stuff that we're doing actually is hidden within comments itself, rather than sort of changing the language proper. Finally, we're going to sort of handle the basics that you're going to need to do. So, pulling in data sources, saving data sources, doing some basic filtering. One thing that I definitely did want to do is actually sort of the ability to do grouping operations. So for instance, oftentimes, like if I'm dealing with a Canada-wide data set, they're sort of divided by territory and all that. And it would be very convenient to have the thing sort of realize, oh, hey, we're going to, group it by territory and all that, and run the model multiple times. Sort of, filtering and feeding in the necessary data as we go. That way, it sort of saves me from having to write, one model per province, essentially. So, all right, to accomplish that, we've got a couple of things to sort of do things. The most front-facing stuff are the actual annotations themselves that are added to the stand file itself. These are sort of split into 2 categories: the external ones and the internal ones. The external sort of deals mostly with data and sort of the sources that are coming in and out, filtering and all that. Sort of, it does a lot of the heavy work itself. The internal ones actually sort of deal with connecting that data to specific spots within the stand program, or exporting it from those specific points out. And that's sort of, if you're just sort of using this as an outsider coming in, that's really all you sort of need to know about it. Now, of course, to sort of support the automation and stuff, that was a goal in here. There's a lot of other backend stuff too. There's a configuration file that makes it pretty easy for administrators to come along and change things, or even just single users to sort of adapt how things work and make it work a little bit more efficient to you. Because we are going to be interfacing with potentially sort of, proprietary or private information and all that, we need some way to store credentials. And to sort of support a lot of the things we want with model reuse and all that, we actually want some sort of cache as well too. Probably the best spot to start off with are the internal ones, since they're relatively simple and easy to understand. Basically, when we're defining sort of a stand data type on here, we add a comment immediately after it, a one-line one. And the first part after it is just in simple square brackets. This denotates the unit that is involved with it. That's really just sort of it for the internal annotations themselves. It's a comment that's tacked on there. There are some strict requirements for it. You can't actually do assignment, for instance. I can't have, assign and declare at the same time. And I'm sure a lot of people will complain that, oh, hey, you're forcing me to put units on everything and all that. Why exactly are you sort of forcing that? Well, part of the problem is just a very simple task that we're actually dealing with day to day when writing these models is time series. Stan has no understanding of strings, but oftentimes, when people actually have a time series thing, they'll actually throw the time in as a timestamp. we need some way to actually convert that. And depending on, the thing you're using, there can be different formats that are convenient. Oftentimes, seconds is a pretty standard way to actually represent time within computers themselves. But especially with compartmental models, we often sort of use days and weeks. So at minimum, we need to have some way to actually take a timestamp like this and convert it into a time. And preferably something which can be disambiguated. So for that reason alone, we need some sort of unit conversion within the system proper. And of course, if we've got sort of vector data that we're feeding in as well too, we need some way to actually feed in, okay, how long is this vector itself? Stat unfortunately does not actually have support for automatically sizing things to sort of what's within to the vectors that sort of are within it. You actually have to manually supply it, which is sort of an annoyance for a lot of Stan users themselves. But the annotations, the backend code behind the annotations is smart enough that if you actually use this special variable called, if you use a special unit called a count, it will fill that in for you. It'll actually go along and say, oh, hey, we've got this vector here. I'm feeding in a bunch of data. I'm going to figure out how long that data is, and I'm going to fill in that value for you. Again, saving you time and allowing you to actually sort of use this stuff without guessing and checking just how many sort of individual counts that are there. Again, more use for actually, adding units themselves. And of course, it's important just to sort of get standardized units as well too. I'm reminded of the probe that the spacecraft that crash landed on Mars because someone screwed up their units conversions. We find this is something which is underappreciated by scientists in general, but well appreciated by engineers, is you always want to get your units right. And certainly, if we're running a model, involving temperature, for instance, and we're switching between data sources between Canada and the United States, we're going to be dealing with Fahrenheit versus Celsius, for instance. It'd be very handy to actually have, some sort of standardized support for that within your code itself. So standardize within the code to use Kelvin. And then outside, have Celsius or Fahrenheit or whatever, and just have it automatically converted for you. This also means that if you switch the data sources and all that, you don't have to switch the model. I don't have to say, okay, well now this data source that I'm using, is in Fahrenheit. I've now got to write a conversion routine for it. No, you just sort of leave it, these annotations like this, grind through them, and it'll, the annotations will actually handle that for you. You don't have to actually sort of rewrite your model on the fly. Now, obviously, people, even with these sort of advantages for it, are just going to hate the idea of, there isn't any sort of, I don't have any sort of natural unit for this. And that's fine. You can actually create your own custom units. This is literally just me sort of surrounding it with quotes to actually say, okay, this is a custom unit and all that. And essentially what happens is the unit conversion system sort of takes a step back. It will enforce that if you're sort of going from one, thing to another, it uses the same custom unit, but it's not going to do any actual conversions for you. So you can just sort of use this as if it was a comment, essentially. And now you're sort of forced to document your code, which is always a good thing, essentially. And that's really pretty much it for the internal annotations themselves. As sort of a quick summary, they are mandatory. They do allow, you actually have to have them if you're going to get any data in and out. There's quite a bit of flexibility with them. If you do change them, you do have to recompile them, but that's probably a good thing in general, because if you're changing your units, you're obviously changing the code itself. So that's okay for that actually to sort of happen in that case. The external annotations are treated a little bit differently. They're actually embedded within a sort of block comment, which can be located wherever you want within your code. I imagine most people will sort of put it at the front. The behind the scenes, it doesn't really care where you put it. You can put it at the back, in the middle, doesn't matter, whatever. This actually has a very standardized format, literally just sort of external data annotations, blah, blah, blah. And the actual content within here is in simple YAML form. So in essence, we're actually sneaking a secondary file within this first file itself. And the idea here essentially is this actually can be stripped away and the other data sets sort of thrown in there. So that way, say, I've got this model that I actually run, but I want to switch the data inputs that are to it. I can actually change this part right here, and it won't count as a change to the model itself. Behind the scenes, that first part is actually just stripped away entirely before deciding, okay, is this a new model or something different? And this means then that you can just very easily change the data sources and not have to recompile the model itself. Again, saving you, precious minutes while you sort of change things around and experiment with it. So these external annotations, as mentioned before, sort of control data proper itself. There's 5 major categories for it. 4 of them are probably, the ones you'd sort of expect to encounter. We need some locations for data themselves. We need some way to filter things, and obviously inputs and outputs, which in this case are called, data and stored. There is an obvious 5th category. Since we're trying to do everything in a single stand file, how exactly you're going to tell stand to run your program, or how are you going to tell it to compile your program? That's actually sort of external information, which is outside the stand thing itself. And so there's a 5th thing in there called stand params, which actually controls those external factors. Sort of walking through them, in order of presentation here. Locations are pretty much as you expect. And it's got a very standardized format. There's sort of an identifier at the front, a little semicolon, since this is YAML. And then it says the type of thing that is there, and it gives you an address for it. So this first one is a CSV file located at this web address. And that's really just the basic format for locations themselves. You can store things, files locally as well too. Currently, there's only sort of 3 data storage things known to stand data annotations itself: comma-separated values and tab-separated values by extension. Parquet data files, which are a little bit more compact and compressible, and definitely, I think, a better supported overall. And finally, CCAN's data store. Since we were writing the dashboard within a CCAN itself, it was kind of important to have that for both read and write access. And these just sort of define both inputs and outputs to themselves. There is no sort of, identifier to say what's an input or an output. The idea being that, it's extra clutter, which you can actually sort of figure out on the fly itself. And again, very simple, very, structured and yet very simple format overall. Once we've got our locations, we want to apply some sort of filter to them. And this follows the same basic thing where you've got an identifier tag and then some instructions on how exactly to do it. In this case, we're going to pull from the column called date in the identifier, the location called vaccines, and we're going to look at it within these 2 specific dates. And obviously there's a lot behind the scenes to sort of support this automatic conversion and all that happening. But this, again, sort of fits with the idea of it being very intuitive and easy to use. You can just simply filter by, okay, I want values greater than this, I want values less than this, and automatically, all those values will sort of be pulled in and everything else dropped for you. So, a very common filtering task handled in just, one simple line of YAML. We can also go a little bit above and beyond. We can also check for equality and inside as well too. Oftentimes when we're dealing with, Statistics Canada things and all that, they have a provincial or territorial ID associated with it. And this is just a simple number. So we can actually say, okay, if we want specific things and all that, we just check to see whether or not they're in this category. And while stand doesn't support strings, the annotations actually do. And so you could use a string to actually represent, okay, I only want to say things from, Canada, for instance, within there, and pull it in from there. Again, sort of pulling from the specific thing. And this is the same basic structure repeated over and over again. Identifier, sort of what you're sort of dealing with right here, and then with a comma on here saying it's coming from a specific location itself. Now you can actually go a little bit above and beyond. If you see here, category actually is referenced as a tag itself. And so you can actually do sort of hierarchical sort of filtering, where you do one line of filtering. And, again, this is a fairly simple filter and all that, but we can actually chain them together, and really sort of tidy up the data progressively. Behind the scenes, it's smart enough to know, okay, if we're pulling from this category, this is pulling from this location, so everything you're pulling from must be from this location itself. And this is a different type of filter right here, whereas these ones basically just discard input and don't go on from that. This one here actually will do grouping things for you. So oftentimes within Statistics Canada data sets, we've got provinces and territories listed right there. This will actually take them and basically lump together all the different values it finds within this province or territory, in this case the English version, drawn from that data set, and it'll run the model separately on each of them. So this is sort of like a grouping operation where it'll take your model and run it multiple times on the same input for you. And again, handling all the different lengths and input sizes and conversions for you behind the scenes. So it's a very powerful way to actually sort of take a model and run it, on different sort of, take the same model and run it multiple times on the, different data sets itself. As for the data, this is sort of the final step to actually put things into stand variables themselves. Well, you can do the traditional thing. We're actually pulling from a specific column from a specific location. And again, this right here is not just an identifier, but it also specifically references one of those internal annotation things and all that. So this is actually a variable within stand proper. So this takes the contents of this column drawn from this location and dumps it into this variable right here, doing whatever conversions it feels is necessary. We can actually go a little bit further than that and say, okay, we want this specific column pulled from these filters. And the location actually will just be sort of inferred by the filter contents themselves. And this is just a very simple Boolean language right here. We can actually say, okay, I want something which has been filtered by the target year. So as you saw earlier, it was within a specific band, but not values that we want to sort of ignore. But there's actually an example model, for instance, where I go over a Statistics Canada data set, and they've got this sort of, they've got province and territory data and all that, but they've also got an aggregated category called Canada. So I use that actually to sort of, filter out that aggregated category and just focus on the rest. And this is a very simple sort of Boolean thing, but you can chain as many of them together as you want. And so just by using simple Boolean logic, you can build pretty much an arbitrarily, complicated filter as you so desire. And of course, you can combine all this too and actually clarify, okay, I want this specific thing from this specific location, just in case you're pulling from, say, multiple locations that, happen to be within these filters themselves. And of course, brackets are, allow you to sort of group and categorize things and all that. Overall, it's a very simple language, but also very powerful, for just doing the basic tasks that you would need within the data itself. Now, one problem, of course, is oftentimes when you're running these things, there are specific parameters you want to sort of add within there. So, okay, we're going to assume that, say, the prior for our standard deviation has a specific size, which may or may not be accurate. Or, we're running a SEER model now, and we're assuming that the specific attack rate for a disease and all that. But we want to actually make those changes on the fly. Well, if you actually associate, rather than sort of like use a column and all that, and we just put a number within there, you can actually then have the annotation, the SDA itself, sort of feed that number directly into stan itself. And so now you can actually go along, tweak variable things on the fly, resubmit it, and you're not going to recompile the model itself. A very powerful way to sort of play around with and tweak parameters. And all of these ones, sort of as hinted at before, also support unit conversion. So this allows you to take, again, specify, okay, this is a Canadian data set, everything is in Celsius, or, oh, this is a US data set, everything is in Fahrenheit, and have the conversions done for you by saying, okay, convert from this to this. And very simple, but also very powerful. Now for the outputs, obviously we're dealing with a full posterior in the case of, probabilistic programming. That's usually more data than you want. Typically there's like thousands and thousands of samples on there. Well, we want to try and handle that in some way. Sometimes that really is what you want, and you just sort of want a dump of the posterior, which you can sort of analyze via other means. Sometimes you want sort of like a summary of it. In this case, for instance, we can actually just pull the average value from the posterior itself and dump that to someplace else. So in this case, what this specifically says is the output variable called slope from stand itself. We're going to grab the mean of that across the entire posterior, and we're going to dump it into a column called, naturally, slope. And we're going to send it to this specific location. And this is where we actually determine what is input and what is output when it comes to those locations themselves. You don't have to worry about that. You can the thing itself sort of intuits it for you behind the scenes. So we've got the ability to summarize. This also extends to other things as well too. We can actually get specific percentiles. A very common approach to actually looking at these things is to get sort of like a credible interval for what various values could be. This allows you to fill in arbitrary values for the percentiles, which also gives you the median. There's also a separate median in case you just want that. You can also do conversions on the output as well too, if you so desire. And again, we're sort of specifying the inputs there. If you don't want to sort of collapse the entire posterior down to sort of some summary statistics, you can also sample from the posterior as well too. So for instance, in this case, I've got, I basically take every fifth sample and keep it, store it in this variable right here, and spit it out to a location that I'm going to call posterior. again, very simple, very easy to sort of parse and understand. It, again, this is sort of fitting in the philosophy that we had earlier on. As for the params themselves, they sort of cover what you expect. Oftentimes you want to change the number of samples or the number of threads that you actually use to run your model. You can do all that within there. This also extends to more advanced parameters like the tree depth and all that. You can change those just by adding them under stand params. This also extends to things that you wouldn't necessarily expect. So for instance, I can actually pin a version of stand to this specific model. Since they do come out with new updates every year, this is actually a nice way to sort of make sure you've got some consistency with it. You want to actually have, say, a reproducible build and all. You can pin the specific stand version and say, okay, I want this version and this version only to do it, which is very convenient if you want to have sort of reproducibility within there. Obviously, there's also ways to change the random number seed and all that. But you can also change how the thing is actually compiled itself. Oftentimes, you want a threaded model just to take advantage of multiprocessors. So you can actually tack on, a little thing to say, hey, we want it to compile it with threading support. And now your model will actually be run with threading support. So this is a nice little grab bag, but it really sort of, elevates the SDA itself from being a simple language to being something very quite useful, even to people who aren't necessarily interested in the automation side. And unlike the internal ones, which are very picky in general, the external ones are designed to be sort of loose and flexible. There's a lot of guesswork behind the scenes to figure out, okay, what data source am I pulling from? What conversions should I do and all that? The goal here is to sort of relieve you of that burden, as an author, and feed in potentially fairly, muddy data and get something out of there. It does also follow a basic hierarchy where we've got locations and then filters and then, the data side and all that. There is some strictness to it. So for instance, you can't use the inputs and output. You can't use an input as an output and vice versa. You also cannot mix whether or not you're summarizing the posterior or you're sampling from it. Those have to be in two separate outputs. Generally speaking, though, those are fairly minimal. There is also a configuration file to sort of help run things as well, too. Obviously, if you're running this in like an external Docker container, you want some sort of standardized location for everything to sort of feed the inputs that are there. Even if you just like this idea and you're starting to run it on your own personal computer for your own use, it can be handy to sort of have like a cache just to sort of remember existing models, so it doesn't have to recompile them. And so there's various things you can sort of feed within here. I've got some basic things in there for adding credentials to access various databases and all that. Obviously a cache to keep models that you've got compiled so you don't have to recompile them. And various ways to change how a command stand itself is built within there. And for more on the administrative side, you can actually override various things which people have submitted within their models. So, if someone has said they want, 10,000 chains and all that, you can just override that and say, no, you get, for instance, 4 chains or 4 threads. That way they can't sort of, burn down the system. Credential files are fairly simple overall. Basically, it's just, you've got the data type that's within there, an address that it's located from, and a credential associated with it. These can also read in from environment variables too, handy in a Docker environment. The cache itself is really just sort of what you would expect from it. A lot of these, like command stand pi and all that, actually sort of have an idea that, okay, we've compiled the model once, we don't have to recompile it a second time. And this actually is respected with this too. So you can actually just run, the first thing, it'll actually compile and run things on the fly for you. If it doesn't have that specific command stand version, it'll download it and compile it for you as well too. But once all of that is done, it basically just goes back to the cache and hits that. So it becomes a lot more responsive overall. All right, I think we've still got enough time for example. Yeah, I'll just do a quick run through on that too, since we are sort of coming up on time. And there might be some, questions about, questions within the chat itself. Right now, I've just sort of got a quick little demo set up here of it, where I've got sort of a downloaded version of it. And we're going to go through this basic model itself. If you want to actually follow along with it, this is actually available on the website proper. If you go to the stand annotations itself, there's an examples thing, models, linear trend line. The original one has a lot more annotated. It basically, because I don't have full documentation, you've sort of got to, document via comments and all that on the fly. I stripped out a lot of that to sort of clarify things and make it a little bit easier to spot. But yes, essentially what we're going to do is answer a fairly simple question. Is the age that people give birth in Canada increasing over time or decreasing? So we'll actually pull in the specific StatsCan data set and save a whole bunch of output to it. Since it's going to take a while, I'm actually going to run the thing in the background right here on the right-hand side. Again, still very much sort of a work in progress, but this is just a simple command line thing you can run where you feed it in, a stand model, give it a configuration thing, and it'll just output a bunch of data. And obviously sort of gives you a bunch of, status updates on the side for like how much things are actually sort of going along here. In this case, we are grouping according to where people are within Canada itself. So we're grouping by provinces. And we're doing that trick where we're actually sort of specifying, okay, this is the aggregate data set for Canada, which we don't want. And so we actually say, okay, we're going to pull in, each of the year, age, and the decimal, ratings within it from these things. And we're going to break it up by the individual sort of district, province or territory there. And we're going to block out, all of Canada, the aggregate data and all that. And then, of course, feed in a little thing to say, hey, how far we want to project in the future. We then sort of feed it into these, we then sort of pull out a variety of outputs on here too. You can see there's actually a ton of outputs that I've got right here. And this sort of answers that there's different things we sort of want. Oftentimes we do want some debugging output, but we also sometimes just want to see sort of like a basic summary as well too. If the summary goes weird, we look at the debugging output. If it's fine, we ignore the debugging output, but we've at least got it there as something. So we actually define a number of outputs here for summaries of, hey, we want to find what exactly these slopes are. We want to sort of, have projections saved out here. And of course, a little debugging thing as well too. And then we sort of march through and do our sort of, our outputs within here. So we can get credible intervals, for instance, on the slope, which just we output directly to a CSV file. We can do, our projections to a projections file as well. And this, again, sort of gives you the year that it's expected and the age that we sort of expect that people will be giving birth within there. We also, again, our answer itself, what we really want to answer is whether or not the slope is going to be positive or negative. And so we actually just collect a specific variable, bruise that up a little bit, within stand called positive slope, which is basically just, was the slope positive or not? If it was positive for all samples, this value is going to be 1. If it was negative across all samples or 0, it's going to be a 0. And we then just go and aggregate that across all the posterior and dump that out to confidence. And again, put a standard deviation on it too, just sort of give us some idea how credible it is. And finally, just dump the posterior to debugging as well. Thinning it a little bit to just sort of save a little bit of space. As for the thing itself, this is a fairly standard linear model itself. You can see a lot of the annotations sort of kicking in within here to sort of say, okay, this is exactly what's coming in. A lot of custom ones here, since there's not sort of a lot of real world units other than like counts and all that, which does conflict a little bit with this, but it's fine. We then sort of come along and do a series of transformations on it, rather than just sort of do a standard linear model where you're just fitting a line to it. This actually does a little bit of pre-transformation to put it inside sort of a unit square. And that has a couple of advantages to it. You can actually sort of use that as if it was a correlation coefficient, for instance, since if you've got it within a square, the mean is almost always going to be 1 within that sort of abstract space itself. And the more it varies from that is just sort of a measure of how correlated all the variable is. So it's a nice alternative to that. We go through, we fit all the parameters. Again, here's the actual sort of model that we sort of throw within here. And then we just generate a bunch of things out the other side. Some of these are saved, some of them are not. There's an option here if you want to actually save the angle proper. It's going to need a little bit of formatting if you actually want it out, but I figured some people might be interested in it. And as you can see, it just finished. We had 14 separate groups that it detected within the data set. It went through and it just finished the last group itself here in about 237 seconds. It did have problems with the first group. It just could not come to a conclusion on that, and I think that's because I actually went through and looked, and there's just not enough data points for it to even sort of do a proper model fit. It was missing, the category is missing completely from there. Everything else worked out a-okay, and so it dumped everything into a directory called posteriors. So if I bring that up, you can see a series of CSV files right there. Let's look at posteriors. Linear regression. I think it was confidence, was it? Yeah, so this sort of tells us the percentage of values within the posterior which were positive. And you can see, yeah, the slope was positive for pretty much everything except the Northwest Territories and Nunavut. Yeah, here we actually have a little bit of variation, although you can see that it's still a very strong tendency towards, yes, actually the age that people give birth is in fact increasing over time. So, hypothesis, confirmed with that. We can actually go through and get our projections as well too. These have again, a very simple sort of format to deal with here, where we've got our individual projections down the side here, along with the date that they're associated with, and the credible intervals associated with it. And since we actually did sort of a grouping by, it also dumped in the geography thing that we actually had there. So, here's our proper credible intervals for our first projection and all that for where it could be, and this is specifically for Newfoundland. And it walks through and goes through the entire data set itself. I'm pretty much finished on time right here. So if you would actually like a little bit more information on it, obviously I would recommend going to the repository itself. It is currently live. I do have plans to put this up on PyPy to make it easier to actually install. I did not get that done in time, but it should happen fairly shortly. If not, I mean, this is a public repository. Download, play with it as you want. And yeah, hopefully if you've got any questions, we can fill through and answer them. So with that, I sort of turn things over to the audience.
Thank you, Haysn. Thank you. It was really interesting. You are the expert of STAN.
Yes.
Thank you. It was really interesting. If there is any question or suggestion, please raise your hand or put it in the chat if you are not comfortable. Could you please share the link of the GitHub and this link in the chat if it is possible?
I will indeed. Handle that right now, actually.
Great, thank you.
Here is SDA's home.
Oh, great.
There you go.
Thank you.
That also contains all the examples right there. This also, I mentioned the prime hunting one. This is actually sort of stored within here too. So if you want to run it yourself within SDA, you can. Currently, it's sort of, it tweaks things a little bit to, get it to fit and all that. I do have plans to actually make the things a little bit more expansive in terms of, what exactly is sort of supported and all that. But hopefully, yeah, this gives you some good sort of QuickBooks to go. And I plan on expanding it a lot more and adding a lot more over time. This is just sort of to give you a taste for what actually is possible with it.
I'm just thinking about why I haven't heard from STAN before. Much more. I should have shared about it much more than that. Yeah.
Mm-hmm.
For the
Yeah, and I
Bayesian
think,
studies, yeah. Go on.
oh, and I think even if you're not really interested in the whole automating stand things and all that, it's handy to just have, something we can add to a stand file, and then it does all the sort of pre-filtering for you. Oftentimes when you're writing your own stand models, you get into a habit of, okay, I've got to write a Python code or, R code to actually sort of drive it and all that and do the cleaning. You're free from that now. You can actually just write a stand model and run it. So even if you don't care about that, it's still some value, I think, to most just researchers themselves, just for playing and experimenting with these models.
I was thinking about manual control. In some cases for the Bayesian statistics probabilistic model, if you can do some manual control on the code, it's do you think does it have better manual control in comparison to R package or base package?
Well, I mean, again, those actually sort of call out to various things behind the scenes. So it sort of depends exactly on what you want. Stand, of course, has its ups and downs. It is sort of its own custom language wrapped around C. And so this sometimes means it's very difficult to debug and figure out what exactly is going wrong. Oftentimes, you can take advantage of the fact that you don't necessarily have to run sampling and just sort of say, okay, I'm going to check my math by dumping it out in the generated quantities thing and use that to sort of help debug. It also does support print statements too, so you can actually print out values as they go. But when you're dealing with many different chains and samples, this sort of becomes overwhelming very quickly. So
I was also thinking about discrete parameters. Does it allow interference discrete parameters? Of course, it is, but based on your example, it is really fast and convenient.
yeah, And in fact, one thing I didn't emphasize within there is that there's a lot of other toys you get with Stan itself. Obviously, it's got like the probabilistic models and all that, which you can sample from. You can also sample random numbers from them as well too. But it's also actually got a full model for handling compartmental models, and other sort of, systems like that. You can actually just code up a function to sort of describe the system, the way the system operates itself, and actually get its own internal thing to do it. It's got its own, Runge-Kutta solver. So if you've got an ordinary differential system, you can actually use that to solve things. Obviously, there's some restrictions on it, but in this case, for the deterministic part, I actually just there's no sampling happening within here. It's just solving a Runge-Kutta thing and dumping it out. I should probably revise this, so that some of the outputs could be sort of improved a bit. But again, another example, you don't necessarily have to do probabilistic modeling with it. It's easy to feed in. Just in fact, here's actually just feeding in specific parameters themselves for the ODE model itself, and then just running through it. So you don't have to use it for Bayesian modeling if you don't want to.
So cool. Thank you.
No problem.
I really enjoyed.
Good. Well, I hope people get a lot of good use out of it. It's been a labor of love for a long time.
Yeah, great. Is there any comment or suggestion, question? I think you're done. Yes.
From me, no.
Yeah, with me.
Well, and I do have a lot of plans to sort of upgrade, and well, thank you very much for the compliment there. I do obviously have plans. If you go to the repository and all that, there are a bunch of issues listed with me sort of like going on and saying, okay, I've really got to improve this. One thing I definitely want to do is unit testing. It's since I am sort of aiming at like an academic thing, you want to have something which is reproducible and very dependable and all that. And you can't do that without writing a ton of unit tests. That's something I'm going to circle back and make sure that I actually do, especially with the modular thing. It makes it easy to add on there. But that's just one example of future work that's coming.
Great.
Yeah. And of course, improving the feedback, making it more intuitive, that sort of thing.
Perfect. Okay. Is there any suggestion or question right now?
All
Probably
right. That's cool.
Yeah, probably you will receive some more emails after we post it on the website. Right. If there isn't any question, thank you once more for great talk you have today. And thank you everybody for joining us. Wish you to see you for the next Super Spreader seminar within next 2 weeks. Thank you all.
See you, everybody.
Bye-bye. Have a good one. Bye-bye. Thank you. Thank you, Haysn. Thank you all.
Yep. See you, everybody.
Have a great one.
I will.